thanks so much for such a warm introduction, and thank the Historical Society for inviting me to come here and talk about something that I've been interested in the last few years, and in particular Peter Stansky for inviting me in November, and Charlotte for making some arrangements for me. So thank you very much for inviting me. Now, I have to confess, something you probably already know, I'm not a historian. In fact, I'm not even a writer. My day job is in material science. But I have been, as was already alluded to, I've been with the department for over 60 years, counting my days as a graduate student. So I've been around here a long time. And in that time, we've had a few celebrations, people retired, where we tried to look back at what had happened, and I was a part of those. So I made various attempts at different times to kind of recollect what had happened in the department. So I was then kind of in the right place at the right time to try to prepare a history. I had known for decades that this was coming, of course, having been founded in 1919. I knew 2019 was the day, and so and some of you have seen this thing that we put together. Now, I started this a few years ago, but I had notes and wrote some things. But were it not for the help I got from the Stanford Historical Society, a number of people associated with the society, particularly Rocky Nyland. I regard this as our book because I would not have been able to produce a book without their help. Okay, so now some of you have seen this book, but not everyone has read the book. So you're going to hear a talk about the book. So it's a little bit like seeing the movie before you read the book, right? And as you would all know, the book is way better than the movie. So I hope you find the book more interesting than hear this movie of the book. So I want to, I hope this isn't too technical. I'll try to stay out of the material science weeds as much as I can to tell you about people that have been, and the book mostly does that. It's about people and events and the doings that led to this department. So I want to, I called it a century of material science. I'll explain that. Well, you already see it there. 1919, 2019. And last October, we had a centennial celebration, and we celebrated this time. So I want to tell you about that century. Now, even before a materials department of any kind was formed, there was a first course in materials, metallurgy, really? And it was in 1903, well before the founding of the department, and it had the title Metallography and Physics of the Metals. Now, you know, physics of metals, that's getting pretty close to material science. And I'll read you this. Work will include, this is from this course, it was given by Dorsey Lyon, and he was an instructor in the Department of Geology, and he said, work will include the study of microstructure of the industrial metals and alloys, and of the influence of chemical composition, thermal and mechanical treatment upon their structure, and also the relation of structure of metals and alloys to their physical properties. Now, as I indicate here, you could hardly create a better working definition of material science for the better part of the 20th century. So this really started early. So now we jump ahead, and the department was founded as a mining and metallurgy department in 1919, and that became, it evolved in various ways, in ways that I'll show. It eventually led to the Material Science and Engineering department. And the head of that department was Theodore J. Hoover, the older brother of Herbert Hoover, who you all heard of, 31st president. So both Hoovers were mining engineers. Theodore had gotten his degree in mining engineering in 1901, and here are the things for which he was known. He later became the first dean of the School of Engineering when it was formed in 1925. So in 1919, there weren't very many schools. There were a few already, but there was not a School of Engineering in 1919. So his department was mining and metallurgy. And then in 1925, the Department of Mining and Metallurgy became part of the School of Engineering, with Hoover serving both as dean and as the head of that the department. So we started there, and we started with Hoover. Now we jump ahead. One of the people that came to personify metallurgy and material science at Stanford was Welton J. Crook. He worked in physical metallurgy, steels mainly. He had gotten his degree in mining and metallurgy from still the geology and mining department in 1911, and he became a steel metallurgist, and that was his game. So here are a number of things that he did, what he did. But what I want to point to here is two things. One, the bottom thing here. He was named for Thomas Welton Stanford, the younger brother of Leland Stanford. They had worked together in Australia. So his father had named his son Welton after Leland Stanford's younger brother. And the other thing I mentioned here, and I put in red, he in 1968, when another professor that I'll mention retired, Welton Crook wrote his own history of the evolution of the field that turned out to be quite useful in what I was able to prepare. So let's jump ahead a little bit. The other person that I want to mention is Shepard, O. Cutler Shepard. He started his work in the metallurgy of gold and silver, and it evolved ultimately into material science, and he became the future department head when it was material science. And here is Shepard on the left here, and with some students, some straggly looking students. There was Theodore Hoover used to complain about that. The way the students dressed, it just annoyed him, the way they dressed. So even by around 1930, they weren't dressing much better. I love this picture because that building is the mining and metallurgy building, and it's the back side of it. And those of you who know this would recognize, oh yeah, it's still like that. So I love that picture. The other thing I like about this picture, the first student here, the one apparently with a cigarette there, that's Alden Greninger. He later went to Harvard and created what was later called the Greninger chart. It was right, Artie. Did you know that? It was a little device by which you could extract the angles between crystallographic planes from spots on X-ray diffraction Lowry spots, and he did that at Harvard, and then later on had a significant career at General Electric, working on nuclear energy. Now, the other thing I'll say here is these are just some of the things that Shepard brought to the department, but he also we celebrated his 90th birthday in 1992. He was born in 2002, and he wrote his own little sketch of mining and metallurgy, which I also used. So there was two documents there that were quite useful in this exercise. Now, let me I've already alluded to this, but the department and its affiliations with different schools was kind of a complicated thing. And I have here a chart. As I've already said, in 1919, mining and metallurgy was formed, and there were no schools that it could join at the time. Standalone department. Then in 1925, the School of Engineering was created, and mining and metallurgy became part of it. Now, Hoover was a mining engineer, and he wasn't so much on the metallurgy part. That's the part that really evolved into material science. So by 1929, they had dropped the and metallurgy, and it was just the mining engineering department. They still did metallurgy, and they were still doing those things, but it was called mining engineering, and it was still in the School of Engineering. And I'll mention this a little bit later, but there was, in the late 30s, there was kind of a tug of war there, because mining engineering here was in the School of Engineering. It was not with the geologists. And the geologists always felt like, wow, mining engineering ought to be closer to us. And there was quite a fight, starting in the late 50s. It got delayed by the war, but by 1947, they had succeeded, and they created a School of Mineral Sciences that included mining engineering with geology and maybe petroleum and some other fields. So at that point then, we are no longer in the School of Engineering, we're in Mineral Sciences. Later Earth Sciences, now Earth and Environmental Science, took on various names as time went on. As did our little affiliation with metallurgy. It was metallurgy, metallurgical engineering. Eventually it achieved departmental status, and in 1958-9, that's when I came as a graduate student. And so my master's degree is from the department at that point. And then finally, and I'll mention this a little bit more, it moved back to the School of Engineering and became the Department of Material Science. And later they added the and engineering, still in the School of Engineering. So it kind of bobbled all around here. It's a complicated history. I'll allude to it one more time. Now, just one picture here. So here's in the 1940s, and here's some faculty in then the the Faculty of Mining Engineering. They'd already dropped the and metallurgy. So it's in the 40s. And the one on the left here is Shepard, and this is Crook. And these are the people that were the foundations that led ultimately to material science. The others here are Humphrey, a mining engineer, Schellinger, an extractive metallurgist, and Tickell, who was head of this mining as a petroleum engineer. So there we were, connected in that way. Another thing I like about this picture, you see the sandstone wall, but I love this picture right here because that 550 is still the number of that building. Was the mining, you can see mining engineering there in that building. It's right out front of the building that I spent many decades in. Okay, now we jump ahead a little bit. World War II, past World War II, atomic energy and the federal support of research is coming into play. And Shepard was the one who first got contracts from Office of Naval Research, Atomic Energy Commission, later NSF, and they worked on problems that had to do with nuclear reactors or possibility of nuclear reactors. They involved metals, liquid metal corrosion and the properties of metals at high temperatures and things like that. And that was pushed by Admiral Rickover. Some of you will remember Rickover, who pushed for nuclear submarines, and that was part of that whole project. One of the students that worked in this area was Thomas Paine, who was kind of the leader among the senior students. Many of them had returned from the war, and there were a lot of veterans in the department at that time. So he was one of the leaders, and he continued being a leader. And at the time he became, as indicated here, he became the administrator of NASA. and he was so at the time of the moon landing. So it's a little thing about successful graduates of the department. Now, I put here in red here, kind of in spite of the engineering relevance. See, at this point, at this time right here, we were in the mineral sciences. We were out not in engineering. So, but in spite of the engineering relevance of Crook and Shepard, at that time, just in 1946, the mining engineering department that they were in moved out of the School of Engineering and into the School of Mineral Sciences, as I say, back with geology. So that's when that move happened, in spite of the fact that they were really doing engineering kind of work. Now, we jump ahead into the 50s, and now we see aerospace and electronics, and as I call the coming of material science. That really developed about in the 1950s. And the architect of this push was really Fred Terman. He was really the architect of modern Stanford engineering, arguably modern Stanford in other ways. And he was always pushing to bring this materials activity back out of the School of Mineral Sciences and into the School of Engineering, where he thought it belonged. It took him 10 years to do that, but eventually he did. So there was a push to bring it back into the School of Engineering from mineral sciences. And the spark that really helped that was the Soviets launching Sputnik in 1957. And I'll say one more thing about that. Now, just at that time, Terman felt like we needed to build up materials, and so he, as provost already, he asked Bob Huggins, who was an assistant professor, untenured even, to conduct a search for faculty members to populate this field that he thought would be important. And my story there is that Terman asked untenured provost, reaches down and asks untenured assistant professor Bob Huggins to conduct this search. And so Huggins did it. And, you know, he did the usual thing of you put ads and you write letters and you get recommendations and you get files and all that sort of thing. And at the end of the day, Huggins ended up with 3 people, and he just couldn't decide which of these that he wanted to recommend to the power structure upstairs. And so he went over to see Terman and said, look, I can't decide. I've got these 3 people and so on. And Terman said, well, leave those files with me here. Let me look at these things. And so he had them for a few days, and Terman then called up Huggins and said, hire all of them. Just hire them all. That's Terman, right? Just let's go. And there are other examples of this at Stanford that you all probably know about, even better than I. But I call that hire them all. And indeed he did. So Sherby and Stevenson and Macris were all hired. Boom, boom. Those were all 3. I don't have a picture of Macris. So in 1958 then, the materials faculty grew from 2 to 5. So a big percentage change there. Now, I've mentioned the mining and metallurgy department. There's a picture of it right there. Our department, mining and metallurgy and later material science, lived in that building for about 90 years or so. So it was Terman's push to bring this field back into the School of Engineering. And so here's an interesting thing, is we had been the Department of Metallurgical Engineering, a department already, in the School of Mineral Sciences. And so we became a Department of Material Science in the School of Engineering. So, you know, we just sort of switched. So it is sort of a play on words there, I guess. So there we were. The department then was material science, it was a School of Engineering, and we were operating in that that building. Now, I mentioned Sputnik. Most people of my generation, and I dare say some of your generations, would know what happened on October 4, 1957, even if I didn't say so. That's Sputnik. The Soviets launched Sputnik. And that was a big deal, as many of you would know. People at the federal level just started running around with their hair on fire. What are we going to do about this? Oh my gosh, we're behind. And so here's just a short list of things that were done. Just a few months later, the President's Science Advisory Committee, called PSAC, published Strengthening American Science. They rung the alarm bells. We've got to do something about this. And one part of this was the creation of an interagency coordinating committee for materials research and development. And that committee recommended that funding go to research activity. Well, I should say that the materials research laboratories be built at universities. Not that it go to industries that are already engaged in this kind of work. They thought that the future would be better if they tried to encourage this activity at universities. And so shortly thereafter, the Advanced Research Projects Agency, ARPA, created in 1958, something that was later called the Interdisciplinary Laboratory Program, IDL, in 1960. And Stanford we were still small, and we couldn't compete quite to make that first club. So Cornell, Northwestern, and University of Pennsylvania were the first participants in this big program. But Stanford made it in the second year, and that then created the Center for Materials Research. So by this time now, in 1961, we have a material science department, and we have a center of materials research. So we're ready to roll, and roll they did. I call that an explosion of faculty appointments in material science in the 1960s. And so these are all of the people that were appointed in the 60s. And I'll just give you the numbers first. We earlier were at 2 faculty, then went to 5. But now with all of these, we're now at 12 faculty. Now, one of the things that I mentioned when I show this slide is there's me in 1963, and of course you all immediately recognize me, right? You're not supposed to laugh. But Professor Bienenstock, Artie Bienenstock, is right here. He looks a little more like he did at the time. This was before Artie helped to found the Stanford Synchrotron Radiation Laboratory and then lead it for about 2 decades to international prominence. Okay. Now, we also, at about that time, as a part of what I've just said, we benefited kind of from the demise of industrial research laboratories. Prior to about the early 60s, industrial companies would have, and did have, well-funded fundamental research laboratories. Many companies had those. And that started for various forces there, it's another story. But there was kind of a demise of the industrial fundamental research laboratories that we benefited from. So Bube and White and Spicer and Tiller and Jabal and Bates all came during this period of time from these industrial laboratories. The focus still, though, was on material science, and I'll come to that in just a second. Now, let me just tell you a couple of things about what went on in the department. One of the very significant events in the department was the creation of Failure Analysis Associates, a company that investigates accidents and failures and figures out what happened. And Alan Tettleman was the ringleader of this. He and John Shine and Marsh Pound and two others at the Oasis in 1967 each chipped in $100. There were 5 of them, so that's $500. And so we're going to start this company. And that company is now called Exponent Incorporated in Menlo Park, I guess. And last time I looked, it had revenues north of maybe $300 million. So it's a big deal that happened. And so here are the participants, the key person being Alan Tettleman, who sadly and ironically was killed in a plane crash as he was going to investigate another plane crash. So how could this be? 1978. And here is Marsh Pound with a number of students that were helping in this project. They didn't all work necessarily for failure analysis, but they did lab work and helped do analysis of failures. So that was one thing. Now the other thing I want to mention briefly, something I called almost a Nobel Prize. Herb Maruska, who's that person right there, he had come from RCA. He was a graduate student of Dave Stevenson's. And he was working on, and he developed a blue, really a violet, light-emitting diode, an LED. And he did that in 1972. Now that's important to be able to have a blue LED because red and green already existed. And so with those 3 colors, you could create white light and you could have flat panel displays. So it's a big deal to get a blue LED. And here's the paper that they wrote there. And there's Dave Stevenson, that's his student. This is Bruce Liebert, who helped in this project also. That's significant in part because in 2014, these Japanese that are mentioned here actually were awarded the Nobel Prize in Physics for the development of the blue laser. Now, it had been perfected many, many times since that early work, but that's why I say almost a Nobel Prize. Now, I mentioned microstructure as one of the founding things in material science, and so you need microscopes to look inside materials to see what's there. And so I just want to show a couple of pictures here. In the first half, or maybe even more than first half of the 20th century, optical microscopy was the principal tool by which you looked at microstructures. And so here's Welton Crook, who I mentioned before, using what we called a bench metallograph. And here's Cutler Shepherd with a student, also using optical microscopy. And this is about the time I came here. We prided ourselves in, gee, we got a new microscope. That is really great, you know. And so we even shined up the room and took a picture of it. This is a big significant deal. But by the late 50s and early 60s, electron microscopy, transmission electron microscopy had come to the fore. Cutler Shepherd had encouraged the development of electron microscopy by a person in electrical engineering. He didn't have a full appointment in electrical engineering, but he worked there, and his name is Ladislas Martin, and he was a pioneer in microscopy and created the first images of biological samples. And then later, well, here's another picture. Here's Craig Barrett. Some of you may know Craig Barrett as a name. He later on became the CEO and chairman of the board of Intel. And here he was as a faculty member doing electron microscopy. But most of the microscopy that was done was later then done by Bob Sinclair, who came. And here's Ann Marshall and Eileen Coe, who work with now very modern instruments to be able to look at every aspect of materials. Now, let me just mention another thing. This one I call solid-state electrochemistry and the coming of lithium-ion batteries. Bob Huggins, who I mentioned before, started doing work on solid-state electrochemistry using various elements and looking at various kinds of reactions. And one of the things he looked at was the lithium-silicon system, which became the foundation for lithium-ion batteries based on silicon electrodes. Much later on, when Yi Cui joined the faculty, he joined up with Bob Huggins, and they wrote this now seminal paper on lithium-ion batteries based on silicon nanowires. I won't take you very deep into the weeds here, but what happens is when you put lithium into silicon, there's a tremendous expansion that takes place, about a 300% volume expansion. And if you do that on a solid piece of silicon, it just all crumbles up and it just breaks apart. So their idea is to create silicon nanowires with space in between them. So when you lithiate those, they can swell and then contract and swell and contract without this principal failure mechanism. Now, the last thing I'll mention here is that Stan Whittingham was a postdoc with Huggins in the early 70s. And after leaving Stanford, he joined Exxon, where he developed a different kind of lithium-ion battery, the one based on titanium disulfide. And he shared in the 2019 Nobel Prize in Chemistry. So there's a link it all started way back here with solid-state electrochemistry and led to the batteries, which is, as you know, is a pretty big deal. Now, another development that I'll mention here that caught a lot of attention at the time was Oleg Sherby's work on kind of rediscovering Damascus steels. He found a way to take really high carbon steel that has 1.6% carbon. Now you say, well, 1.6 doesn't sound like very much. That's a lot of carbon. If you put that much carbon into steel, it's usually just dead brittle like glass. But he found a way to do it with his colleague Jeff Wadsworth. He found a way to do it and to make the particles of iron carbide very small, so that under the right conditions, it wasn't brittle, it was actually super plastic. You could take this stuff and just pull it like chewing gum. And he claimed that this was the basis for these Damascus swords, and he had various pieces of evidence to back up that claim. Now, it wasn't all just work, and in fact, in the book, I try to write about how things were a little quieter in those days, and we had more time to enjoy things in those days. And we're all of us, were subjected to this tremendous pressure in all kinds of ways, and we don't do as many things quite like we used to do them. So I'm just going to show a couple of things on sports. So there was a team in 1968 that happened. The dislocations. That's the name of a defect in a crystalline solid. Something that I taught for about 50 years. They were the touch football champs, and here they are all, mostly from our department, not all. And the fourth one over is the Craig Barrett that I mentioned before, later CEO of Intel and chairman of the board and so on. So there was time to do that. I remember at that time, about that time actually, at lunchtime, we would go out and either play volleyball for an hour and then come back and get back to work, or in some cases, I remember going out with Craig Barrett, and he was quite a track athlete, and I remember going out and watching him high jump 6 feet. Now, it was long, that was far away from a world record, of course. But 6 feet, you try jumping over 6 feet. Very tough. I could barely make it over 5 feet. Which I was quite proud of, actually. But he was, yeah. So, and then he would throw discus and various things. So things were a little quieter. Here's another example of athletics and team sports. Well, this isn't really a team, but this group of students, 6 of them, they are students, challenged the faculty to a relay race. This was in 1973. So here mostly are the faculty, and then here are the students that are going to run this relay race. Now, they didn't have enough faculty participants, so Steve Robinson here, I mentioned here, is a ringer. He was a postdoc, so we granted him tenure for a day, and, so he could be there. So here they are, and there's Craig Barrett, there's the ringer, there's Dave Stevenson, Oleg Sherby, Bob Huggins. These are the 2 that he hired, and then Clay Bates. Those were the faculty, and then these are the students. They run this relay race. It's a 1.5 miles, so that means each person runs around the track 1 time. It's a 1/4 mile. 6 of them make 1.5 miles. And I have one picture here taken mid-race. And at that point, Bob Huggins is leading the student here. So at this point, the faculty are winning, so to speak. But they lost. But it was great fun. Now, the other thing I've written about and I like to mention is the pioneering women that have played an ever bigger but still not big enough role in the evolution of our department. I called them pioneering for reasons you'll say. The first was Janet Zaff Briggs, who got a degree of engineer from the mining engineering department in 1933, and she went on to a very distinguished career. She was a member of the Mining Hall of Fame, for example. So she had a very, very distinguished career in industry. But then there were no women at all until the early 1960s. And these are some of the first students that came for master's degrees in the early 1960s, right here. So these were pioneering women. They were entering a field like many engineering fields that just didn't have very many women in them. That's still true. It's changing slowly. And Carolyn Fouts and Alice Fisher Colbury, who later on worked with Artie Bienenstock for her PhD, are shown there also. They were undergraduates here, and they both stayed on for graduate work as well. Now, the first woman to get a PhD from our department was Emel Kikinli, a Turk. And she got her degree in 1973. That was the very first one. There had been none before then. And here's a little chart showing the disparity here. Here's PhDs granted to men. It really got off the ground here in the late 50s, about the time I came. And there was this gap, and it was the early 70s when a few PhDs were granted to women. And it's growing in this estimate here, maybe 4 per year compared to 18 per year for men. And until recently, or a decade and a half ago, there were no women on the material science faculty. But finally, Sarah Heilshorn joined us as the first woman to join our faculty. And she was followed not long after, in 2010, by Jennifer Dione. So there are then now 2. Jen Dione, I mentioned this because she just has received, last fall, she received the 2019 Alan T. Waterman NSF Award of $1 million toward her research, and it's the highest award for a scientist in any area under the age of 40. So it's a big deal. So we were extremely happy. Well, we knew that this was a possibility because of the quality of our work, but we were pleased at that result. Now, I've been talking about a little bit about research in the 60s and 70s. Most of that is research with graduate students, and in fact, we had neglected the undergraduate program in that period. And this chart here really shows it. It's the cumulative BS degrees granted from the department in its various incarnations from the beginning of time back here. And right here in the 1970s, where it was so tough for those young women, the one or two that we had, we were graduating almost no bachelor's students. And this got us into trouble. This led to a loss of one billet and no net faculty growth for 2 decades. So we sort of got ourselves into that problem, and I'll show how we got out of it. I don't want to leave you with that negative story because we got out. I'll come to that in a minute. So the other thing that we didn't do well, and in the book I talk not only about the triumphs but the tribulations and the problems that we had also. That's also documented in the book. And one of the things that we did not do well, we had not embraced materials issues in silicon technology. We were, attending our own thing, and we had things that we were interested in, and we did them, but we weren't paying attention to what was important in the Valley, and in particular, silicon technology. But we responded in the 1980s. John Brodmann came and started doing work on electronic materials, silicon-related. Stig Hagstrom came and worked in surface science that was on the interfaces that were important in that kind of technology. And Bruce Clemens came and started work on the thermodynamics and kinetics of thin films and fabricating films that are pertinent to silicon technology. We also developed, I cut a couple of slides out here, we also developed a major effort in the mechanical properties of thin films. Many faculty were involved in that. And so we did change, and we started responding to these changing conditions. Still there were troubles. I call it, and I write it like that in the book. There were troubles for an aging department. Now we're in the early 90s, and the big burst of faculty appointments occurred in the 60s. So that's 30 years before. So those people are starting to retire. Well, two things. You see here that the faculty headcount hardly changed over nearly a 2-decade period. So we knew that trouble was coming. Now, I like to, or I don't like to, but I do point out that I became the chair right about there. And when I became chair, all things went to a hell in a handbasket. And I think I stopped being chair right about there. So much from a chairmanship, right? But we did make then, started to make what you might call aggressive plans to, some of which were joint appointments with other departments to connect ourselves better with other activities at Stanford, and more involvement with other engineering departments. And that has brought about a rebirth of the material science department. And that's been led largely from this point onward. It's been led by John Brodmann, Bruce Clemens, Bob Sinclair, Paul McIntyre, and Alberto Soleo. So those are the people that have really pulled us out of this ditch that I left us in when I left. Yeah. Now, so there are so I call this rebuilding for the 20th century, And that started in the 90s. I mentioned the joint appointments. Sean Wong joined us with a joint appointment in electrical engineering, Fritz Prinz jointly in mechanical engineering. And then Rainer Dausgaard came to work on mechanical properties, which we badly needed by that time. And Paul McIntyre worked on electronic ceramics, which we also badly needed at that time. So that was the beginning. We set that. But then, in the beginning of this century, there was another explosion, a big explosion. So these are all of the faculty that have been appointed since 2000, in the last 20 years. So there's tremendous growth in this time period. And I just call your attention, we won't go over all of these, but I just call your attention to, so here's Mike McGee working on solar cells. Here's Milosh working on biology. Here's Iche working on energy and environment. Here's biomaterials, nanophotonics, energy production and storage, and even neurotechnology, even. So I call these now are activities that are addressing pressing and exciting societal problems. And it's different from what had gone before. And the last thing I'll show then is I like to contrast what is happening now with what had happened through most of the 20th century. And this goes back to the kind of basic definition of material science that I gave early in 1903. And so the traditional definition of this field of material science and engineering, perhaps in modern form, I'll read it, is the synthesis, processing, modeling, and characterization of useful engineering materials to control their properties and behavior through the control of composition and microstructure. That's similar to that one that Dorsey Lyon wrote in 1903. And I call this, by contrast, I call this engineering of materials, where the aim is to go inside and manipulate and make materials better for someone to use somewhere, somehow. And to that definition now, I think we now should include the following. This is to be added to that. Utilization of materials and material science to address pressing and exciting societal problems in technology, the environment, biology, and medicine. And I call this engineering with materials. So there are materials, the behavior is known, and now we make use of those to solve these important problems. So that's a change that there are certain elements of the field that are struggling with that change, to be honest. But it's a fundamental change that's happened in the last 2 decades. So finally, I'll just say thank you all, Stanford Historical Society, for contributing to this and for helping to write that. First and foremost is Rocky Nyland, who was she was formerly the content editor and essentially helped me write the books. And as I've said many times, she helped make a silk purse out of a sow's ear. I was the one that created the sow's ear. And Jean Deacon, who she works with, served as this really great text editor, and she could make my engineering words sing. Ralph Simpson, who also worked with Rocky, turned the draft into a polished book that you see in the formatting and the laying out through his extra. And thank you, Karen Bartholomew, kind of oversaw this whole activity and provided key advice, different junctures, and sort of oversaw the project from start to. That's why I put you at the bottom. So thank you very much for hearing my story.
So we do have time for a few questions if anyone has one. If you can wait for a microphone so that your question is recorded for posterity, that'd be wonderful.
Today, is there more focus on for product design and engineering in terms of materials, the choice of materials, so that when the product is no longer needed, it can be remanufactured, recycled, reclaimed, remarketed?
Those are important elements in the field. I can't say that we have strong activities in those areas, but if you go around the country, you will find just those issues being addressed in material science.
With Provost Terman and the creation of SRI being a bridge between the theoretical and the applied, do you think that helped material sciences, and do you think it is missing today?
Well, that's a good question. I haven't really thought much about that. Of course, I know those events, and I know the linkage between the university and SRI. SRI has, at least as far as our department is concerned, been kind of separate and apart and unconnected. We have friends there, and they do work of interest to us, but I don't know whether that kind of initiative would help us. I'm not so sure.
Question.
So I'm one of those middle 60 kids. I graduated in electrical engineering in 66, and I liked material science so much that I TA'd the Engineering 50 class my senior year, and I thought the students were excited. I can't understand why it leveled off with the undergraduates.
Well, I think that was more what we weren't doing. We just weren't nurturing that group. We weren't out recruiting and doing the things you have to do in order to continue bringing people in.
Yeah. And you mentioned the Alan Waterman Award. He was actually my undergrad advisor.
That's his son, I think.
Okay, well, the old man
Yeah.
from the early 60s working in the AEL building or something.
Right. I believe that's the Alan Waterman. Alan T. Waterman. Artie can correct me, but I believe the one who was on the faculty here was the son of Alan Waterman, who was the first director of the National Science Foundation.
And I remember those exciting those exciting additions to the faculty when Art joined with the CMR and Huggins and so on. It was good. And Tettleman was my advisor back in those days.
Right.
A question up here at the back.
You talked a lot about trends within material science, Sputnik kicking off a lot of innovation, different shifts within the department, etc. But you also talked a lot about people, different leaders, different scientists. Do you feel that one or the other had a stronger impact on the department? And do you have a sense of going forward how to manage that, how to hire the right people or how to get ahead of major trends?
Yeah. If I knew that, I would be the dean, I suppose. I don't know. It's hard to say. If we take the Sputnik as an example, there was Terman who was his own force, and those just happened to coincide. So together, those things. There are many. Sputnik happened, and the really rapid development of Stanford in this area didn't happen everywhere. So it was Stanford, it was Terman, who even in the late 40s recognized that federal support of research was going to be a major thing. That was even before Sputnik. And so he was already pushing. He was doing all kinds of things that pushed in that direction even before Sputnik. Sterling, too. And Sterling as well. That's right. And Rocky is always reminding me that it's Terman with the help and approval and support of Sterling. Terman, of course, had his own barbed, rough edges that some of you may know about. He went, well, I've already kind of implied that because he reached down and got Bob Huggins, an untenured assistant professor, and said, do this search. And he just zoomed right past the dean and the chair of the department, and he just did it, right? So he was always, in fact, I tell the story in the book there, the business about the department moving from metallurgical engineering in the School of Mineral Sciences and into the School of Engineering, becoming material science. And Terman was pushing for that. And Terman, being the hard-driving guy that he was, he pushed for this. And Sterling wanted to make sure that those folks really wanted to do this. So he actually called Huggins and Shepard over to his office, Sterling did, and said, he didn't say in effect, but he was implying, I know there's this hard-charging Terman that's trying to get you to do this, but do you really want to do this? And they assured Terman that they really thought that was a good thing for the department. But it was one measure of how Sterling would kind of, make sure that Terman was not, ruffling too many feathers.
You mentioned about the neglect of semiconductor and silicon research for a while, but I didn't notice in any of your slides that any emphasis was given to it after that.
Well, yeah, we did do. I didn't include them. There was a whole lot of stuff we did in support of silicon technology in respect to the mechanical properties, something that we knew a lot about. And I could probably bore you with a lot of things that we did there. Now, we weren't making devices. That was outside of our but more and more activity. Paul McIntyre has spent most of his career working on the dielectric materials that make a transistor work, for example. I didn't mention that. It was just under electronic ceramics, but it's in there. So there was a major change. That big activity kind of had its push, and now there are other elements. I mentioned neurobiology and various other directions they're going. So some of the reaction that we did do is now past, and now they're on to other things.
If I remember, Professor Brovman eventually became the president of Bucknell University in Lewisburg, Pennsylvania.
That's right.
Between his being the chair of your department and his taking that position, was he an administrator?
Yes.
Here at Stanford at some point?
He was. Someone can probably correct me, but he held various administrative posts, first in the School of Engineering and then later for the university. And he was like the associate dean or associate provost for undergraduate studies, or some title like that. I don't. So he spent a lot of time really focusing on those things. I don't have his titles right here, but he did.
I have two history questions. Before World War I, circa 1916, thereabouts, Stanford apparently had a very effective but small aeronautics group, which seemed to have disappeared somewhere around 1919 or 1920. And the second question is, was there ever any synthesis between the Defense Labs, Lockheed's Advanced Research Group, and the Electronic Defense Labs in Mountain View and the Stanford faculty?
Well, a limited amount in material science. There was a lot of activity. Many of the faculty that Terman brought here for aeronautical engineering, aeronautics and astronautics in the 50s, they were intimately connected with Lockheed, for example, and NASA Ames. And we never had quite that intimate a connection. We did have we did have people that worked at Lockheed, for example, who would come over and enrich our courses, give courses, so that we had some interaction. Well, it wasn't nearly as intimate as Aero and Astro would have been.